Welcome back. Let's continue our discussion about Open Cavity. Now, I will show you how to run the program Cavity.f. To begin with, the cavity dimension, radius, mode of interest, for example, TE11, and the radius, just like the geometry we saw before, and numerical instructions, etc., are specified in the main program. So main program provide the interaction structure and the radius and specify the mode of interest. And then a guessed value of omega is then input into Muller, which calls complex boundary condition, CBC, to evaluate the value of D. Subprogram CBC calls Runge-Kutta to perform the integration from Z1 to Z5, and subsequently, Runge-Kutta calls differential equation to evaluate the derivatives at every Z step of the integration. Finally, Muller returns the solution for omega, new omega, to the main program, which prints all the information of the interest and call scale or S-plot, S-scale or S-plot to plot simply f of z and phi, complex f of z and phi, as well as omega, r, and quality factor. Common blocks are extensively employed, common variables for the information sharing. For example, the cavity dimension should be the same for all the programs specified in the main program, and the field profile calculated in the subprogram CBC should be the same for all the cases between the main program and the subprograms. So let's share the same information. Okay, cavity dimension and calculate the result. Here is the cavity dimension used for numerical example, just like this one. Okay, it's on open cavity. And the result, well, we will obtain f as a function, f absolute value as a function of z, we obtained. And phi, the phase, as function of z, okay? And for this case, we also obtain the resonance frequency. For the cutoff TE11, the cutoff frequency should be here. Radius 0.9 is here. Radius is here, 0.9 centimeter. Substitute, this is x chi-mn 30 over 2 pi. So we got the cutoff frequency. And TE111, 1 is the first actual mole. So field profile just like this one. TE11 L equals 1. TE111 moles field profile and phase angle as function of z for the cavity shown above. Here is the result we want. And wall resistivity and loss factor is the conductor. The interaction structure, the cavity is made of copper or any kind of metal material, metallic material. Omega loss has been included in the cavity code, Fortran code, through subprogram rho and C loss. Formulation of the wall losses can be found in Appendix E, and if possible, you should study by yourself. As a first exercise, we can ignore this effect to simplify the result. Hence, rho and C loss by setting the wall resistivity to 0 in the main program to simplify the calculation. Okay, TEMM mole dispersion relation for a vacuum field waveguide changes slightly because of the skin depth. Okay, as shown here. Okay, let's help us a lot. Check the validity of the result. We should always check the convergence. Numerical result is not always correct. Therefore, we should always be careful. When calling Muller to solve for the root of a function, for example, CF in always monitor the number of times, how many times you iterate, your iterations. I count in Appendix B that the function has been evaluated. For a well-behaved function, the number should be small, not too long, not too much. Okay, when the number becomes too large, and in the case Muller is unable to find a root as warning sign, warning signal of some numerical difficulty due to, for example, erratic behavior of the function, discontinuity and sharp spikes, or the presence of the main closely spaced roots, the result may be in question, or the physics may be unexpected. The warning signal cannot be ignored. Very important. After Muller returns a root, always ensure that the resulting function value, for example, value 1, value 2 in Appendix B, is vanishingly small, converge relative to the large terms of the function. For example, if the function is composed of terms of the order 10 to the power of 10, a function value of 10 squared, okay, may be considered vanishingly small. Okay, check the convergence. A valid root is not necessarily the desired root. For example, we provide a guess value for the L equals to root and call Muller to search around it for the correct L equal to root. Muller may return a different root, such as L equal 1 or 3, if the guessed value happen to be a better guess for that root. A reliable way to verify the L number of the root returns by the Muller is to count the number of peaks in versus Z in a profile f of Z versus Z. Even with all these checks, there is still no guarantee that the results are free from numerical errors. We must also check whether the step size in a Z integration is sufficiently fine to ensure convergence of the results. Okay, so we should check if more steps. In principle, it should be more accurate, such as here. As we increase the number of steps, total interaction section is divided into IG steps. More steps, which means each step is small enough and the error is small. However, if the step is too much, the error will be accumulated. So, too much step is not always good. Depends on your computer, the function of your computers. For this case, number of steps, increase the number of steps seems to be obtain a better result. Okay, does the numerical result make sense? Always check. Even compute correctly, numerical result cannot be trusted. Be careful, unless they make sense physically. So be careful about your calculation. You may start by asking some universal question, such as in the energy conserved, such as do the result reduce to the well-known limit to some extreme? Do they exhibit reasonable parametric dependence? Do they conform to a known scaling law? Obtain answer to this question is a sure way to become familiar with the problem. We are now ready to go deeper into the problem. For the best reward of all, let us imagine, take us to the unexplored and unexplored territory of the research. Okay, we just provide the software we are using for Cheng, but you can check the result using several methods. You can check with high frequency structure simulator, HFSS, help you a lot. You can rewrite the program by yourself, change to MATLAB or Python. That will help you a lot. So this exercise just provide the fundamental practice, just provide an example for you, and you can change to other form. Here are some discussions. Okay, discussion can be, you should read by yourself. And we have several exercises. For one, I will read one. We have more than 10 things. For the open cavity of figure 1 with the dimension given in table 1, the resonance frequency of F111 mode is 9.839 gigahertz. For an enclosed cavity, a closed cavity with the same radius and length, and the resonance frequency will be different. So explain the difference qualitatively. So one is fully closed, the other is semi-open. Let's see what's the difference. Second, use the program Cavity to show how the quality factor Q of a given mode varies with the output taper angle of the open cavity. So change the angle will change the quality factor. Okay? Why? Interpret the result. Try to answer this result. You have the software in your tool, in your hand. You have the tool in your hand. So you can perform the simulation and try to answer by using with the simulation. Prove your answer using the simulation and your argument. Exercise 3. For the cavity dimension provided in table 1, the quality factor of the first 3 modes L equal 1, 2, 3 are respectively here. Given 2 reasons to explain the rapid drop of Q with the actual mode number from 400 to 56. Change a lot. Why? Why? Try to answer. 4. Using the program Cavity to show how the quality factor of a given mode varies with the cavity length. When the cavity is long enough, the quality, it has the ability to store more energy, and its behavior looks like here. Prove and explain. Okay, that's exercise number 4. Exercise number 5. Okay, try to answer using a well model, a better model. This is the actual cavity, and this is analytical cavity by assuming the reflection coefficient gamma is here just to, and left-hand side is closed, not much difference, but right-hand side with a reflection coefficient gamma, and you can compare the result. It will be interesting and helpful. Okay, exercise 6 and 7. We are going to study this case by an artificial reflection. In addition to this one, we provide another reflection, iris. This discontinuity provides a reflected signal together with the reflection from taper section, and see what's the difference. Exercise 8. Okay, as the frequency change slightly, the field will also change, like this one, and explain. Okay, you can prove this one, this structure, with a high frequency structure simulator, HFSS, because the boundary condition is not sharp, it's open. So the field profile will be sensitive to the resonance frequency. Exercise 9. Okay, we can do the same thing using spectral response, and spectral response will be discussed very soon. Exercise 10. Exercise number 10. Write a computer program based on the spectral domain formalism in section 2 of Appendix F to answer the following questions. RFS2. You can use the existing program or write the program by yourself. Exercise 11. Okay, exercise 11 is a pretty good chance to compare the time domain and frequency domain result, spectral domain result, and you will find it's different. It's different because time domain result, we make 3 assumptions, and this assumption is oversimplified. And if we want to consider a complete model, we should consider the non-uniformity, the change of mode, and others. Okay, that will be very useful. Exercise 11, very helpful for you to understand the resonance frequency and quality factor